Alrighty, morning everybody. Welcome back to Calc 3. By the way, if you all ever want to talk about classes, I will be doing like a thing at the start of, once the official course schedule comes out, I'm going to talk about kind of what classes are coming up and which ones in the math department are good fits for sort of a post 320. But if you have any questions in the meantime, I'd be happy to answer them. Plan for today is I've got a quiz for you on Standard 7, then we're going to jump into Standard 8 and start talking about derivatives. Usual office hours this afternoon, 2 o'clock, tomorrow morning at 10:30, and tomorrow afternoon at 1. And I did post some Standard 8 questions late yesterday afternoon if you want to start taking a look at those. Any questions or comments before we get started? Including on, like, classes or whatnot. Yeah, come on. Oh yeah, I still need to respond to the emails I've gotten about that. Currently it's looking like yes. Will it be, I think you also asked in your email, will I be offering a hybrid or remote options? Not sure yet. I'll have to get back to you on that. Other questions? Okay, in that case, let's go ahead and do the, oh, before I forget. 2 lines are outside, but suddenly it starts raining, and I mean it's a downpour coming on down heavy on those 2 lines. What should they do? Those 2 lines should coincide. Okay, here is the quiz for today. I'll start this into the room. Go ahead and take about 10 minutes as per usual. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Okay. Alrighty. So today we're finally going to start talking about how to do derivatives of multivariable functions. So just give you a heads up, this standard is probably going to be a 2-day standard. Meaning we'll work through this packet today and Friday, and so you can probably expect the standard 8 quiz will be on Monday. Before we start going into multivariable derivatives, I'd like to do just a little bit of review of what a derivative is from Calc 1, sort of look at the one-dimensional example before, or the two-dimensional picture of a derivative before we move on to 3D and higher. So let's say we wanted to look at the function f of x equals 2x cubed, and the value a is equal to -1. Meaning, if we were to sketch a graph of this, we would get a graph of our f of x that looks something like this. And if we were to pick a point, say at a equals -1 on our graph, I'd like to talk about how do we find the derivative there. But before we talk about how do we find the derivative of this function at a equals -1, I'd like to talk just briefly about what does the derivative represent geometrically. So if I were to sort of ask you the question, not looking for a number here, but what does f prime of -1 represent? What would this tell us about if we knew what the derivative was at -1 for this function? what does that actually tell us about the function? What? The slope of, sorry.
The slope of the line.
Yeah, exactly. It's going to be the slope of the tangent line to our function at a equals -1. So in other words, if we were to sort of draw out a line, like so, the tangent line to the function x equal f of x at -1, the slope of this line would be equal to the derivative. So in other words, f prime of -1 is the derivative of f of x at x equals -1, which is the slope of the tangent line to f of x at x equals -1. Kind of informally, it's basically how steep is the function at that point. How fast is the function increasing? Looking at this tangent line, looks like the tangent line should have a positive slope, meaning as we go from left to right, our y values on the tangent line are getting higher. So if we wanted to actually compute what is f prime of -1, well, I think we should start by finding f prime of x. So if our f of x is 2x cubed, what would our f prime of x be? I mean, how would we differentiate 2x cubed with respect to x? Uh-oh, count one question. How horrifying. Yeah, 6x squared. How did you find 6x squared? Yeah, so you use sort of the power rule, in other words, which said if you differentiate something like x to the n, you bring down your exponent and then subtract 1 from the new exponent. Yeah, that's exactly right. So in this case, if f of x is 2x cubed, f prime of x is going to be 3 times 2x squared. We bring down the 3, subtract 1 from the exponent, which is 6x squared. And this tells us a general formula for f prime of x. And now we can plug in -1 into this formula, and we'll get 6 times -1 squared, which is going to come out to a positive 6 for our derivative. Meaning, this tangent line that I drew right here should have a slope of positive 6, delta y over delta x. It looks more like a slope of 1, but that's because I didn't really draw this to scale very well. But it is positive, which is something we knew our slope should be from just the general shape of what the tangent line looks like. Let's say we wanted to actually go a little bit further, though, and find an equation for the tangent line. We know what the slope of the tangent line is, that's 6. So what could we do, Laurie, if we wanted to find a general equation for what the tangent line would be? Ooh, okay. So start out by putting it in point slope form, which I think is nice because we know what the slope is. I think we should be able to find a point in our line without too much hassle. And then we could simplify things and get everything in slope-intercept form. Yeah, that sounds like a good strategy to me. One thing we need to do before we start using point-slope form, though, is we need to know a point that's on our line. How can we find a point on our tangent line here, which I'm going to call L of x? Jackson? Plug in which point?
The x point. So you plug in -1 to f of x.
Aha! Yeah, because this point is both a point on our graph of f of x, and it's going to be a point on our tangent line. So if we can find the y-coordinate of this point by just finding what f of -1 is. F of -1 is just going to be 2 times -1 cubed, Negative 1 cubed, 3 negatives becomes negative. It's going to give us a negative 2, meaning the y-coordinate of this point is at negative 2. And now we can use that to find the equation for the tangent line, doing what Laurie suggested by starting by putting it in point-slope form. Which, if you don't recall, the point-slope form of a line is y minus y naught is equal to m times x minus x naught, or m is going to be the slope. X naught comma y naught is a point on our line. So here we know that negative 1 comma negative 2 is a point on our line. So we could plug in negative 2 for our y naught and negative 1 for our x naught. Our slope is just going to be the derivative, what we found here, so 6. And then from here, we have something with just y and x in it that we could simplify and put in slope-intercept form if we want. This is going to give us y plus 2 is equal to 6 times 6x plus 6. And if we were to subtract 2 from both sides, we get y is equal to 6x plus 4. And this is going to give us the formula for a tangent line to the function f of x at x equals negative 1. I'm flying through this pretty quickly, but that's because I expect that you've seen this before in Cap 1. This may be a little bit of a reminder. But any questions about how we found this tangent line? In general, if we rewrite this form of point slope, if we kind of replace y naught x naught y naught with our point a comma f of a on our line, and replace the slope m with just f prime of a, we can rewrite this point slope formula to get y minus f of a is equal to f prime of a times just x minus a, where a is sort of the x-coordinate of the point where we're taking our tangent line, in this case negative 1. And then if we simplify, or if we add f of a to both sides, we will end up with y equals f of a plus f prime of a times x minus a. And this is going to be our general formula for how to take a tangent line to a function f at x equals a. L of x is equal to f of a plus f prime of a times x minus a. And depending on who you took Calc 1 with, you may have heard this called the linearization of f of x at x equals a. Linearization hits the name L, corresponding to the fact that this is a tangent line to our function. A line that's going to share the same slope as our function at x equals negative 1, and also passes through the same point, negative 1 comma negative 2, as our original function did. So this formula is kind of important, so I'm going to write it up in the top left corner here so we can come back to it later. But in general, the slope is just, the derivative, geometrically at least, is just giving us some sense of what the steepness of our function is. How steep is this function at the point negative 1? Meaning, what's the slope? So, we're going to refer back to this later, so I'm just going to write it up here for now. Any questions before we move on, though, to looking at the multivariable version of the derivative? Alrighty, so next thing we're going to do, we're going to compare this to a function going from R2 to R. Our f of x here was just a function going from R to R, but we're interested in multivariable functions in this class. Let's say we're looking this time at a graph of the function. And this is going to be a function from page 2 of the handout. If you want to follow along in your packet. We're going to look at the function f of x comma y is equal to x minus y squared plus xy at the point 0, negative 1. So I went ahead and plotted this curve on the screen, z equals x minus y squared plus x times y. Gives us something like this. And the point that we're looking at x comma y equals 0, negative 1, I plotted right here, this black dot. It says 0, negative 1, comma, negative 1, corresponding to the fact that if we were to plug 0, comma, negative 1 into our function f, the z coordinate that we would get as our output is also negative 1. Let you check that if you want. And the question is, I want to talk about the slope of this surface at the point x comma y equals 0, comma, negative 1. So in other words, the derivative, the multivariable derivative, we'd like to be able to tell us some information about how steep this slope is going to be at this point. There's a problem, though, with trying to ask this question. In Calc 1, you could just say, oh, the slope is sort of this rise over run, how steep the function is going from left to right. Why isn't the derivative for this function just going to be as simple as, here's a single numerical value telling you what the slope, what the steepness of this graph is going to look like? Question?
The slope is different for different directions.
The slope is different for different directions. Sarah, is that what you're going to say?
I'm going to say you can theoretically approach it.
Yeah, just like when we were talking about limits and we saw you can approach a point from infinitely many directions, you could talk about taking a slope of this function in infinitely many directions. You could talk about, for instance, what's going to be the slope of the function if we were to travel just from in this direction on this point. If we were to just kind of travel along the side of this mountain-like shape, going this way, in which case the slope is actually going to turn out to be 0. It's going to be flat. We could also talk about what's going to be the slope of the function at this point if we were to travel this way, kind of travel up the hill a little bit. This way, the slope's probably going to be positive if we're going up this way. And so we can't just talk, and we could also talk about what happens if you go in the steepest direction, straight up the hill or straight down the hill. The point is, you can't talk about the derivative as just being a single number anymore at this point, due to the fact that it matters which direction you're traveling in, or which direction you're looking at this point, in order to talk about what the steepness is. In a couple directions, this way and that way, it's just going to be flat. But if you were to go up the hill here, it would be a positive slope. It's just a couple examples. And so the multivariable derivative is actually going to be a little bit more complicated than the single variable derivative, because it's not just because we're going to end up needing multiple values for what the derivative is equal to. Specifically, when we look at finding derivatives, we're going to be looking at what happens if we were to try and find the slope if we went in the same direction as the positive x-axis, or if we were to travel in the direction of the positive y-axis, meaning parallel to the positive y-axis, what are our two slopes going to be? And to answer that question of what are our slopes going to be going to in the direction of the positive x and the positive y-axis, we're going to need a notion of something called partial derivatives. Let's go back to the board here for just a second. And I'm going to write this out over here to the side so we can kind of refer back to it as we look at our example here. So in general, a multivariable function is going to have multiple what are called partial derivatives, where the partial derivative is just going to be the derivative of your function looking in a single direction. So back on the front page for just a second, we can say, given a function, f going from Rn to R, meaning today we're going to be focusing on functions that have vectors as inputs and just scalar values as outputs. On Friday we'll talk about what happens if you have vectors as outputs. We can say that the partial derivative of f with respect to a variable, which I'm going to call x sub I, is going to be given by the expression del f sub del xi. This fancy symbol here is not a backward 6. It's called del. And it's always going to be used to refer to when we take a partial derivative like this. And it's going to be the derivative of f. So here we're thinking of f as being a function that takes in n variables, x1, x2, up through xn. But del f, del xi is going to be the derivative of f with respect to the variable x sub I. Meaning, if we treat x sub I as a variable and all other x sub j's as constants. So we'll talk about what that means here in a second when we look at an example. If you remember in Calc 1, we actually had a way to define the derivative, probably how you initially saw the derivative, using a limit. In Calc 1, you may have seen something like f prime of a, or let's say f prime of x, is going to be a limit as h goes to 0 of f of x plus h minus f of x, all divided by h. We have a very similar formula for the partial derivative of f with respect to a single variable xi. And that's going to be taking a limit as h goes to 0 of f of x1, x2, etc., x sub I plus h up through xn minus f of x1 through xn, all divided by h. Or if you remember, in Calc 1, the way this h variable worked is if you're trying to find the slope of a function at, say, this point here, if this is your x, then typically x plus h is going to be some x-coordinate of a point really close to x. And so basically, you're taking the slope of the secant line between f of x and f of x plus h. The slope of the line connecting these 2 points is just going to be given by this. And then you just take a limit as h goes to 0 to find the derivative in terms of a limit. Same's going to be true here, except if you have a function that takes in input vector, a vector with multiple components, x1 through xn, the partial derivative as a limit is just going to be add h to only to the ith component here, and then subtract off f without adding h, divide by h, take a limit as h goes to 0, defined in a very similar way. So let's actually take a look and see what happens if we try and apply this to this specific function, to f of xy equals x minus y squared plus xy. Now, back on page 2. So if this is going to be our function, since this function takes in vectors with 2 components, an x component and a y component, we're going to have 2 different partial derivatives for this function. The partial derivative of f with respect to x, and the partial derivative of f with respect to y. And the way you calculate each of those, no, I'm probably never going to make you take a limit like this, because these kind of get nasty, is you do this procedure. When we differentiate del f del x, we're going to be differentiating f with respect to x. Meaning we're going to treat y as just being a constant value, and x as being the only variable that we're differentiating with respect to. So here, if we were to differentiate f of xy with respect to x, well, the derivative of x with respect to x is just going to be 1. Y, we're going to treat as a constant, and if we're differentiating a constant, negative y squared, with respect to x, What do we always get when we just differentiate a constant term by itself? Huh? It's going to be 0. So when we're taking del f del x, the minus y squared term, and I guess we could say minus 0 squared if we want, it's just going to go to 0. How about x times y? If we were to differentiate with respect to x, meaning we're treating x as a variable and y as a constant, what would the derivative of x times y be with respect to x? Huh? Is that what you're going to say?
Yes.
I agree. The reason being is if we were to differentiate something like 2x with respect to x, we would just get 2. The x goes away. If we were to differentiate something like negative 8x with respect to x, we're just going to get negative 8. If we were to differentiate y times x with respect to x, in the same way, we're just going to get the constant out in front of the x, which is just going to be y. And here is our del f del x. Our partial derivative of f with respect to x is 1 plus y. Del f del y, on the other hand, we're going to have to do a little bit differently. Now, we're going to treat y as our variable, and x is just being a constant. So does anybody want to take a stab at figuring out what del f del y is here? If we're differentiating x minus y squared plus xy, but this time treating y as our variable, and x is just some constant value that's coming along for the ride. Take it?
0 minus 2y plus x.
I think so, yeah. X is just a constant, so if we differentiate with respect to y, we're going to get 0. Negative y squared, when we differentiated with respect to x, it just became 0, but with respect to y, we can use the power rule, and we'll get a negative 2 times y. And when we differentiate x times y with respect to y, I agree, we're going to get an x. For the same reasoning as before, but in reverse. 2y would differentiate to get 2. Negative 8y would differentiate to get negative 8. X times y, if we're differentiating where y is our variable and x is a constant, it's just going to differentiate to give us x. So our partial derivative, del f del y, is going to be negative 2y plus x. So if we were to try and look at that, plugging these in at a specific point, like 0, comma, negative 1, we can actually plug these into our partial derivative functions. And the way you might expect, you would plug in 0 for x and negative 1 for y. So if we were to take del f del x and evaluate it at the point where x is 0 and y is negative 1, what would that come out to? If we plug in x equals 0 and y equals negative 1 into our formula for del f del x. Tim?
0.
Yeah, we're going to get 1 plus our y coordinate, which is negative 1, which is going to be 0. And if we were to take del f del y of 0, comma, negative 1, what would that give us instead? We're going to plug in 0 for x and negative 1 for y into our del f del y formula. Ever? We're going to get negative 2 times our y coordinate, which is negative 1, plus our x coordinate, which is 0, which is indeed going to come out to be a positive 2. So del f del x gave us 0, and del f del y gave us 2 when we plugged in our specific point into the functions del f del x and del f del y. So what does that represent geometrically? Well, we pull this back down for a second. the values of del f del x equals 0 and del f del y equals 2, what that really tells us is that if we were standing at this point, 0, x equals 0, y equals -1 on our function, and if we were to travel in the direction of the positive x-axis, meaning we were travel parallel to the positive x-axis, so this way, we would have a slope of 0. The fact that del f del x is 0 tells us just traveling parallel to the positive x-axis is going to give us a slope of 0. I need more board space here. I'm just going to receive that. So, write that down in words. Del f del x at 0, -1 being 0 means if we travel in the direction of the positive x-axis, on the graph of f, starting at the point 0, -1, the slope, or the steepness, in that single direction is going to be 0. So del f del x being 0 just means if you travel in the same direction as the positive x-axis, our surface is just going to be flat in that single direction. So, with that in mind, what do you think the fact that del f del y being a positive 2 is going to tell us? If we were to say the fact that del f del y at 0, -1 is a positive 2, how could we make that into a geometric statement about how this surface is behaving?
If this is based off of what we said about del x, I guess I would say if you travel in the direction of the positive y-axis from the point 0, -1, this will in that direction.
Bingo. In the direction of the positive y-axis, at the point 0, -1, we'll get a slope of positive 2 since del f del y at 0, -1 came out to a positive 2. So if I plot that one, we could sort of see how if we're traveling now along the red curve, in the direction of the same direction as the positive y-axis, it's hard to rotate this the way you want, we're going to have a slope of positive 2 because we're going to be walking uphill at a steepness of 2 units going up for every 1 unit we go in the direction of the positive y-axis. And so these del f del x and del f del y values that we found are really just telling us 2 different values for steepness if we were to go towards the y-axis versus towards the x-axis. And if we were to travel in other directions, like say straight up towards the top of the hill up here, we would be able to get different values for the slope as well. Those are going to be a little bit harder to find, and it's going to be a couple standards from now before we're ready to talk about how do you find the slope in other directions. But you can find the slope in other directions as well. But in the direction of the x versus the y-axes, to find your slope, you just take del f del x, del f del y, and plug in your point. Where the partial derivatives we're finding by saying, I want to treat one of my variables as a constant and differentiate with respect to the other variable. Del f del x, we treat x as a variable, differentiate with, and y as a constant. Del f del y, we treat y as our variable and x as our constant when we're taking our derivatives. Stop for a second and I'm going to ask again, what questions do you have about all this? sort of giving us a three-dimensional analog of what does it mean to take the derivative on your graph of your function if we're traveling in different directions. Ooh, the plane. So it's sort of the plane where the vector heading in this direction and the vector heading in that direction are going to be.
Yeah. What, like, is that a thing that you can do? And what would that tell you?
That is totally a thing you would do. That would give you what's called the tangent plane. And we're actually going to talk about that on the next page.
Oh, alright.
I was going to say, that's a good question. Like, and it is something you can do, is something that's going to tell you lots of information about the function, and is something I want to definitely spend a good amount of time looking at. Any questions, though, before we, other questions before we move on? All right, so I'm going to mute this again for a few minutes. Let's talk about the question that Emily just proposed. How do we find sort of the tangent plane for a graph in R2, we had a tangent line. We're going to have, it turns out, a tangent plane to our function for a function going from R2 to R. But before we do that, I want to talk about the derivative without specifying a direction. The reason why these del f del x and del f del y are called our partial derivatives is because when we define the derivative of our function as a whole without specifying which direction we're looking at, we're basically just going to be making a matrix that's made up of these partial derivatives. So, first of all, we're going to say that a function f going from Rn to R is differentiable at A at a vector A. A here is a vector like 0, -1 that we can input into the function. Some value in the domain. If two things happen. First of all of the partial derivatives, if you have a function from Rn to R, you're going to have n partial derivatives. All the partial derivatives, del f, del xi, evaluated at A, have to exist. Meaning if you take del f del x, del f del y, potentially del f del z, del f del w of your function, you always have to get things that you can plug in A into and get an output that makes sense. The other thing we're going to need is that all the partial derivatives not only exist, but have to be continuous at the vector A. Meaning, when we take del f del x, del f del y, etc., these all need to be functions that are continuous at A, which is what we talked about on Monday, the idea of continuity, where they exist at A, the limit of each of these functions exists at A, and the limit is equal to the value of the function at A. So, talk about what's the actual derivative. Derivative is just going to be an 1 by n matrix which we're going to denote as being df of A. And the matrix we get when we differentiate here is we're going to be del f del x1 of A, del f del x2 of A, all the way up to del f del xn evaluated at A. In other words, it's just a matrix of all the partial derivatives. Dr. Gerstle, you're using different notation than you are in your handout. In your handout, you're saying like f sub x1 of A, f sub x2 of A, up to f sub xn of A. That's a different notation for the same thing, the partial derivative of f, with respect to variable x1, x2, etc., evaluated at A. Over here, instead of saying del f del x at 0, -1, we could have also written f sub x of 0, negative 1, and f sub y of 0, negative 1. It's just a different notation that the book also uses to refer to partial derivative. Partial derivative of f with respect to x at this point, partial derivative of f with respect to y at that point. So the derivative is the matrix of your partial derivatives. The gradient is going to be the same thing, but written in vector form. If you want to talk about the gradient, instead of writing a d, you sort of have this upside-down triangle-like thing, f of a, and that's just going to be a vector in Rn that has the same components, all of your partial derivatives evaluated at a. So del f del x1 of a, comma, del f del x2 of a, comma, etc., del f del xn evaluated at a. So the derivative is going to be a matrix. The gradient is going to contain all the same information, but it's going to be a vector instead. And as we're going to see later on, sometimes it's nice to have the matrix version, and sometimes it's nicer to have the vector version. For being able to do things like taking products of matrices is going to give us like the product rule for multivariable functions. Whereas the gradient is going to allow us to do things like take dot products, which is going to be helpful. And Emily, getting to the question that you asked earlier, how do we find, say, the plane that's tangent to our curve? We actually have a nice formula for how to do that. Our tangent plane formula. And I'm going to say tangent and put in parentheses hyperplane. Because if we're looking at a function from R2 to R, it's going to be a plane. If we do it as a function from R3 to R or R4 to R, it's going to be something called a hyperplane instead, which we're going to talk about on Friday. And the formula for this is going to be h of x1 through xn is equal to f of a, what you get from plugging in your vector a into the function, plus the gradient of f evaluated at a dotted with the vector x minus a. Which, if you wanted to write out, is the same as saying f of a plus f sub x1 of a times x1 minus a1 plus f sub x2 of a, x2 minus a2, all the way up to f sub xn of a, the nth partial derivative at a times xn minus a. So question. There you go. I was trying to decide you were doing a little hand stretch there.
I'm good.
Does this formula look familiar to anyone? Particular, and I see you nodding your head. Is there anything else currently written on the board that this formula for a tangent plane looks an awful lot like?
It looks like the modification of the Flintstone form that we did on the first page.
Yeah, this looks a lot like our formula for the tangent line to a function, to a two-dimensional graph of a function. This was our two-dimensional tangent line function, f of a plus derivative times x minus a. It's essentially the exact same formula, f of a plus gradient of f dotted with x minus a. It's just that this time, everything that we're going to be looking at, the gradient, x minus a, are going to be vectors instead of scalar values. But otherwise, it's basically the exact same formula. Any questions or comments? So let's see what happens if we start trying to take the derivative, gradient, and tangent plane to this function we were looking at on the last page. And if you go to page 4 in the packet, I give you space to do it for the exact same function. So for this specific function, I'm going to just write it up here. We know that our partial derivative of f with respect to x at 0, negative 1 is 0. our partial derivative of f with respect to y at 0, -1 is 2. And f of 0, -1 came out to be -1. These are values that we've already found by taking partial derivatives. F of 0, -1 being -1 is just plug in 0 for x, -1 for y into the original function to get that. Let's see if we can find what the derivative, gradient, and tangent plane are going to look like here. If we wanted to take the derivative of our f of xy here at the point 0, -1, we're going to get a matrix with 1 row and 2 columns in it, where our first entry is just del f del x at A, del f del y evaluated at A. Here A is 0, -1. And what two numbers are going to go into our matrix here? For partial derivative of f with respect to x, partial derivative of f with respect to y. No? 0, 2. There's our derivative of f at the point 0, -1. It's not a single scalar value like it is in Calc 1, but in fact it's going to be a 1/2 matrix where the entries of the matrix are just going to correspond to these partial derivatives. The slope in the x direction at that point, the slope in the y direction at that point. How about our gradient? We were to take the gradient of f evaluated at f, or the gradient of f evaluated at 0, -1. Remember we said that's just going to be a vector whose individual components are the partial derivative of f with respect to x and the partial derivative of f with respect to y. I'm trying to mix up the different notations here so that you kind of get used to what do they look like. Which vector in R2 is going to give us our gradient vector? Keeping in mind that we said the components in the gradient vector are the same as the entries in the derivative matrix. Okay? It's just 0, 2. Yeah, just the partial derivative of f with respect to x, partial derivative of f with respect to y. The exact same as the derivative matrix, except the gradient is going to be in vector form instead of in matrix form. And now, because Emily is so eager to do it, I'm going to rewrite this down here, 0, 2, give myself a little more space. We're going to find a formula for the tangent plane. And so the tangent plane, using this formula for h of x1 through xn, so in this case just h of xy, is going to be equal to f of a, so f of 0, -1, plus the gradient of f at 0, -1, dotted with the vector x minus a. So dotted with, in other words, x comma y minus 0, -1. Which if we start plugging in values, we can plug in f of 0, -1, it's just -1. The gradient vector we just found was equal to 0, 2. And how can we simplify x comma y minus 0, -1? How can we rewrite this as just this difference of two vectors as just being a single vector? Whoop.
Wouldn't it just be x, y plus 1?
X comma y minus -1, which is the same as x comma y plus 1. You betcha. So that's going to be our tangent plane. H of xy is -1 plus 0, 2, dotted with x comma y plus 1. Now, we can take the dot product. We'll get 0 times x plus 2 times y plus 1. Which, if we write out, is just going to be negative 1 plus 2y plus 2, which is the same as 2y plus 1. And here, we can replace h of xy with just the variable z. Treat this as a function of x and y like we normally would in terms of thinking about graphing it. And that's going to be our tangent plane. Z is equal to 2y plus 1. And before you all go, I want to show you a picture of our tangent plane and how that corresponds to the actual wake up graph. So z equals 2y plus 1. If we go ahead and graph z equals 2y plus 1 on top of what we already have, here's what we get. The purple is the tangent plane here. If we got rid of the function, if we got rid of the original function, we could sort of see this looks like a plane. And the thing about this tangent plane is just like how the tangent line happened to match up with the original function, and had the same slope. If we take a look at our tangent plane, if this is our function, z equals 2y plus 1, and we call this h of xy, what would del h del x be if we differentiated this 2y plus 1 expression with respect to x?
Zero.
2y plus 1, just constant plus constant. Differentiate with respect to x, we get 0. Del h del y, we're going to get 2. The same values that we got for del f del x at 0, negative 1, and del f del y at 0, negative 1. And so the fact that this plane is tangent to f of xy, what that really means is that the tangent plane has the same partial derivatives as the original function. Same partial derivatives as f of xy at the point 0, negative 1. But the difference is the tangent plane is a plane. And I would say and passes through the same point. Meaning it passes through the point 0, comma, negative 1, comma, negative 1. But the tangent plane is a plane, and meaning it has the same del h del x and del h del y everywhere you look, whereas del f del x and del f del y were not constant functions. The partial derivatives of f were dependent on which point we picked. So I'm just going to end with what is a plane. Okay, that's going to do it for today. When we come back on Friday, we're going to talk about how to find partial derivatives of functions from Rn to Rm, and also start looking at what does it mean to take a hyperplane as opposed to just a plain old tangent plane. Have a good one, everybody.